Hello, this is Fatima Mohabi, and the topic of my presentation is Cognitive Network Management in a Sliced 5G Networks with Deep Learning. So network slicing is a network architecture in 5G that allow the network infrastructure to be divided into slices, and each slice is assigned to a service. So each slice can be customized to the need of a service. So for when we use network slicing, we need to do resource assignment and manage the resources between all the slices. So we need to measure the traffic data, and we need to identify the demand patterns and kind of predict their future demands. So this resource management needs to be cost efficient, and there already are some tools, mobile traffic data analytic tools that do this resource management. However, they have some limitations. The first thing is that they all use minimum absolute error as their loss function. So they use this loss function to kind of avoid service level agreement violation. Service level agreement violation is when the service cannot get all the resources they want, which is very costly. So these methods, to avoid these violations, they accommodate the offered load all the time, which is not efficient. And the second thing is that when we have network slicing, this prediction needs to be done at slice level. But these current predictors, they evaluate the demands over all the services and not at the slice level. So here, DeepCog, which is the cognitive network management using deep learning, trying to kind of remove those limitations. So this method predicts the amount of resources for each network slice in order to minimize the economic cost. So they are using deep learning, and the loss function they use is customized based on this network slicing, and they're not using minimum absolute error. So they're trying to balance between over provisioning and demand violation. So over provisioning is when a service is receiving more resources than they need. So we are wasting the resources. So we don't want over provisioning, and we don't want demand violation at the same time. So this method operates at data center at different points in mobile network. So here you see an overview of this method. Here you see that the input is slice traffic. This slice traffic is converted to tensors, and the tensors are fed into the neural network. The neural network uses the loss function for training, and the output is the prediction of the demands or the prediction of the future demands for a specific network slice. So this neural network tries to minimize the over provisioning and maximize the quality of service for service. So here we see some notations. So in the network, we have N stations, we have M data centers, and each data center kind of service the some number of stations that they are assigned to this data center. So here delta shows the traffic for slice S at the station I at time t, and this vector here shows the total traffic for a slice S over all the stations at time t. Similarly, demand of a slice S at data center J at time t is shown here. As you can see, it's the demand for a slice S at data center J is a summation for all the stations that they are assigned to that data center. So this is the summation of the traffic over for that slice for all the stations that they are assigned to that data center. So here you see the total demand. So total demand for slice S over all the data centers at time t. And the capacity of slice S at time t at data center J. So, and this is the total capacity over all the data centers. So this neural network tries to predict the capacity based on T snapshots. Here you see the traffic of a slice S at time t minus 1 to time t minus t. And the loss function is L, which uses the ground truth D to make this prediction C, which is the capacity. So they're using encoder-decoder in the decoder in their neural network. As you can see here in this figure, encoder consists of 3 layers of 3D convolutional neural networks. So for this layers, they're using ReLU as the activation function, and also to fight overfitting, they use dropout at the second and the third level, and dropout rate is 0.3. So the decoder is a fully connected neural network, which means all the neurons are in one level, are connected to all the neurons in the next level. Again, they're using ReLU as the activation function here, except the last layer, which they are using a linear activation function. So for training this neural network, they are using a stochastic gradient descent with Adam optimizer. As we know, gradient descent tries to minimize the loss function at each iteration by tuning the model parameters. So here I mentioned that they convert the slice traffic to tensor. So we are going to see how they do this, because then they feed a matrix to neural network. So in here, we are going to see how they convert the traffic to matrix. So here they do like a projection of traffic to a tensor in a way that they want to put all those stations that their service demands are highly correlated next to each other as neighbors in the tensor. So here you see total traffic at the station I, which is shown like this. So the traffic at station I at time 1 to time t minus 1. And here, which this traffic at time at station I at time t equals the summation over all the slices for that station at time t. So to do that projection, they're calculating the similarities between two stations I, j. So here, using this formula, this function, which measure the similarities between two time series, they measure the similarities for station I and station j based on their total traffic. So then at the end, we have a distance matrix T, which shows that the similarities between each two stations. Then they compute the virtual bidimensional coordinate pi, which is like more like reducing the dimensionality, because this measurement is a matrix and they're trying to project it in bidimensional coordinate by using this function here, minimizing the distance or the differences between these two measures. And then they are matching each entry of their final input matrix with pi. So they are assigning each entry of a matrix with a pi. So as I mentioned, they want to put the station that their demands are highly correlated next to each other as the neighbors in the input matrix. That's why they're trying to minimize the cost when doing this assignment, which the cost is the Euclidean distance between the neighbors. So here, KIE is the cost of assigning PI to entry E, and XI can be 0 or 1 if the PI assigned to E is going to be 1, and if it's not assigned to E, it's 0. And we need to pay attention that to each entry, only one PI is assigned. So as I mentioned before, this method tries to balance between over-provisioning and the demand violations. So based on the notation, if CJS, which is the capacity for slice S at data center J is less than the demand, then SLA violation happened. And in the other way, if the capacity is more than the demand, then we have over provisioning. So they use this difference between the capacity and the demand as part of the loss function, because they wanted to use a stochastic gradient descent. We know that the loss function cannot be a constant, so they cannot assign constant values as the penalty for both SLA violation and over provisioning. So they are using this epsilon or E here, which is a very small number, to kind of bring this X, which is the difference between the capacity and demand, into the penalty. So this is here, this is the loss function. So the loss function for the capacity and the demand is the summation of the penalty over all the data centers. So here they compared their method to the other methods. So as you can see here, this kind of lighter shade of color is SLA violation cost, and the darker is over provisioning cost. You see that for this method, which is shown in orange, the SLA violation cost is way lower than the other methods. However, the over-provisioning cost is almost lower for all of them. So here you see that they are evaluating all these methods on different slices and different services. Here they use YouTube, Snapchat, and Facebook, which each of these services they have different demands. So this difference between the performance, you can see that for SLA violation cost, deep cog, this method outperform other methods. However, considering over provisioning, it doesn't do that good. And the reason for that is that this method tries to make a balance between these two. However, the other method cannot consider one of them more important than the other one. Then there are considering some different approaches to kind of see and compare their method to these approaches. So they add an offset to traffic prediction. So here for the first one, MAE post, they adding 5% offset to predicted traffic. For the second one, they find the best offset, like with just looking at all different offset values that they can apply and pick the best one to minimize the loss function. The third one adds the offset at training step. So they add this offset to the loss function and not the prediction. And for the last one, they are adding over provisioning value picked by this method to predicted value. They are mentioning that these two MAE post-best and pre-best, they are not really efficient and kind of feasible to do. So comparing this performance to this one is still their method outperform these approaches. So in conclusion, as you see, this method outperform the other predictors, kind of they try to minimize the cost with balancing between over provisioning and SLA violation, and it kind of accommodate the capacity prediction to different network slices.